Chemistry Life Knowledge, where today we are going to explore all about water. And so, as you know about water, we have hydrogen oxygen molecules combining. We have it's H2O, so we have two hydrogens, one oxygen. And we talked about how it was a polar covalent binding that's happening. And so we end up with little Mickey Mouse ear looking water molecules. Okay. And so on the hydrogen side of the molecule, there is a slight positivity, and on the oxygen side of the molecule, there is a slight negativity. Okay. And this lends us to form hydrogen bonds between various water molecules, and that is super important. Also recall, whereas covalent bonds are stronger, hydrogen bonds are super weak, so they are easy to break, but also means they're super easy to reform. And so this is happening constantly in water. Now, when we talk about water, the root word for water is hydro. And if you're attracted to water, you would be a polar molecule because water is a polar molecule. And so then we would say you are hydrophilic. So all of our ions, because they have, whether they're positively charged or negatively charged, they can be attracted to either the hydrogen positively charged side or the oxygen negatively charged side portion of water. So all those ions and polar molecules are called hydrophilic. Now, molecules that are not ionized and are not polar, they do not want to interact with water. And so they are called hydrophobic molecules. And so we'll be coming back and talking about this all semester. So looking at water, there's quite a few unique properties of water. We're going to go through, I think it's about 6 of them today, some of them briefly and some of them in a little bit more detail. And the first thing is, as we all know, water can exist in 3 forms. We know it can be a gas as in steam. We know it can be a solid as an ice, but at room temperature, it is liquid. And if we look at water, like at a lake or river, pour it into your glass, you can see that the water is moving. And that's because those very big hydrogen bonds are constantly forming and breaking, forming and breaking, forming and breaking. That's what gives water its movement. So it looks like this little thing where the bonds are forming something and then breaking, forming and breaking. The second thing about water, and you know this if you ever put a pot of water on the stove, and you're waiting for it to come to boiling so you can make your tea or your coffee or whatever, it's very slow to heat up. But conversely, we also know many of us have burnt ourselves because we thought, okay, I turned that burner off 10 minutes ago and put our hands on the pot, and we can burn our hands. And that's because water has a tremendous capacity because of these breaking and reforming bonds. It can absorb a tremendous amount of heat, but it also can release heat if it needs to. And those two things help prevent temperature change. The third property of water is called cohesion. Remember, co means together, prefix meaning together. And what this means is water molecules like to stick to each other. And this creates something called surface tension. So if you've ever been at a waiter, or if you've been at restaurants where the waiter is annoyed at you, you know that you can slightly overfill a cup without spilling a drop on the table. Now, the person with the overfilled cup cannot move that cup without spilling it, but you can annoy them no end by filling the cup more. And this creates surface tension, which allows, little bugs to be able to walk on water. Now, cohesion are hydrogen bonds with water molecules attracting to each other. And that is different than adhesion, which is the hydrogen bonds of water forming with other substances. And so you can see this if you look at the dewdrops in the morning and they're attached to the plant. Or for instance, if you put a paper towel in a liquid and you can see the water going up the paper towel, that is due by adhesion of the water molecule to the paper towel. So let's review that terminology real quick. Cohesion is attraction. In this case, we're talking about water between water molecules, but other molecules can have cohesion, like for instance, liquid mercury in the old school thermometers. Mercury coheses with each other, and that's what forms the little beads on the surface. And if you have little beads, you can put two little beads together and have them touch each other and form a bigger bead. Now, don't break up the mercury thermometer and do that because mercury is toxic. Okay. But that is cohesion, not to be confused with adhesion, which is where different molecules are stick to each other. So think of adhesive tape. That tape sticks to the paper because of adhesion, and that's why it was called adhesive tape. Now, looking at water, realize that a single water molecule can do both adhesion to a different surface as well as cohesion with other water molecules. Because you can have polarity on both sides of the water molecule. Now, one thing that's interesting is looking at the interface between the liquid and the air and what is happening to the water molecules on the surface. If you look here in the liquid, you will notice that a water molecule can form like 4 different bonds. So it has lots of bonds, but here at the surface, it only is being pulled by hydrogen bonds in 3 dimensions, and that is what's creating the surface tension on the surface that allows the little insect to walk on the surface. Okay, so let's go back to those properties of water. And the 5th one is a really important one when it comes to science and chemistry and doing experiments, and that is water is a great solvent for polar molecules. It dissolves many things because of its slight polarity, and it allows a solution to form. And so I'd like you to stop this, and actually I will just let it play, and I'll let it play through a second time because this is explaining how sugar, when you dump it into water or into tea or into coffee, how it's dissolved, okay? So the water molecules are surrounding the sugar, and due to the attractions because of the polarity, they're able to pull those outer sugar molecules away from the lump. And eventually they pull until all you have is a little tiny bit left there in the middle. So let's go over these terms one more time. The solute is the substance that is dissolving. So whether it's sugar or it's tang, or whatever it is you are putting into the liquid, that is the solute. And the solvent is the liquid. In this case, we're talking about water, but it could be milk, it could be gasoline, it could be whatever liquid we're talking about. And when the solute dissolves in the solvent, that forms a solution. So if it's sugar in water, that would give us a sugar solution. Now, how much solute we put in it, we can measure, and that gives us a concentration. It could be 1% sugar, it could be 10% sugar, it could be 35% sugar. So if you can dissolve the solute in the solvent, then we say it is soluble. But if that solute doesn't dissolve in, it can dissolve in water, but say it dissolves in water, but it doesn't dissolve in a different liquid, then it would be insoluble to that particular solvent. So just because it can dissolve in one liquid doesn't mean it can dissolve in every liquid. So going back to water as a solvent, most substances dissolve in water, okay? Reason is polar molecules because of the hydrogen bonds. And what happens here is we actually form what is called a hydration shell. So what this is showing is a bunch of salt crystals being dumped into water, and salt is polar, is sodium and chloride. And what you'll notice is the chloride is negatively charged and it's attached to the positive parts of the hydrogen molecule. And then the sodium is positively charged and it's attracted to the negative parts of the little red oxygen molecules. Okay. And so surrounding the sodium, we get a bunch of water. Surrounding the chlorides, we get a bunch of waters. And these are what we call little hydration shells. And as you can see, they can completely cover the surface. And so when we have an ionic compound, which is what sodium chloride was, because of the positivity in the water, that made the sodium and chloride dissociate from each other as well as dissolve. And this is the same process that's going to happen if we dump an acid, like hydrochloric acid, or if we dump a base, such as sodium hydroxide, which is lye. They are going to dissociate in the water. Now, a substance that can both dissolve and dissociate, these substances can conduct an electric current, so we call them electrolytes. Okay, so sodium's an electrolyte, chloride's an electrolyte, potassium's an electrolyte. We've got lots of electrolytes. You'll learn those words when you get into nursing school, for instance, because we look at blood levels of these electrolytes in people. So hydrophobic molecules are not polar. They don't like water. And so what's going to happen, they are going to isolate themselves, and you're going to have a little clump of hydrophobic molecules, and they're going to be surrounded by the water on the outside. And the reason why is because those water molecules are going to form hydrogen bonds with each other, but they cannot form hydrogen bonds with the hydrophobic molecules. And so now we had hydrophilic, we had hydrophobic, and going back to the amphipathic molecules, they're going to partially dissolve in the water. In other words, the polar part, the heads of the phospholipid membrane, are going to form hydrogen bonds with the water, and the tails are going to be repelled by the water, and they are not going to form bonds. So you can form a phospholipid bilayer, as we see in a lot of our organelles, or we can just have a single layer with the heads on the outside and the tails on the inside, and then we can have something non-polar there in the middle. And we have these in our body as well, but you just haven't talked about them yet. We'll learn about them later on this semester. All right. Now, the last property of water I want to talk about is that solid water floats on liquid water. In other words, ice floats. We kind of all know that. And the reason for that is when ice temperature lowers, those bonds are stretching out with each other. And so here is a little animation showing they've moved further apart, and they're not nearly as mobile as the temperature goes down. And so they are going to form a solid that is larger than the volume when they were liquid. And so this is why you have to be careful not to overfill your ice cube trays. If you still work with ice cube trays, or for instance, you are freezing a soup, then make sure you keep a ½ inch of clear space at the top, because it's going to freeze. That's why you don't put soda bottles in the freezer unless you want them to explode all over the inside, because soda is mostly carbonated water. So let's talk about some chemical reactions. So chemical reactions are an equation. Okay, and we can write it in the symbols, the chemical symbols, or we can write the names of the molecules. So we can do hydrogen ion plus 2 oxygens, or we can do 2 hydrogens plus 1 oxygen gives us water, or we can write 2H plus an oxygen gives us water. And so we put an arrow to indicate the direction of the chemical reaction. So on the left side of the equation, whether in this case it's water or sodium and chloride over here, these are called the reactants. And these are the things that are going to combine to make the stuff on the right side, which is the product. And so in these 2 equations, we're showing the upper one, we're showing 2 smaller things forming a bigger one, whereas in the bottom one, we're showing 2 big things breaking down to form 2 things. Like, oh, and that's also seen over here where we have glucose, which is going to break down and give us carbon dioxide. So it's going to take 1 of the carbons and 2 of the oxygens And that's going to leave ethanol, which is going to be C4H12O4 is what is going to be ethanol. Okay. So it doesn't matter if it's big or small. If it's to the left of the arrow, it's considered the reactant. If it's to the right of the arrow, it's considered the product. And so when we look at the role of water in chemical reactions, no, most of life is in a watery environment, which means water very often is going to be a reactant. For instance, if we add a positive charge acid with water, or we can have a base where water is going to give up a positive charge, that's going to happen millions of times per day in your blood as your blood tries to keep the pH normal. And it also happens every time we are, for instance, making ATP and breaking down ATP. We have two different types of reactions, and they both are going to involve water. So we will come back and talk about those probably in the next section. So I want to thank you again for all your hard work in this chemistry review, and I will see you as we go on and talking about solutions and mixtures.